Okay, so today what we're going to be looking at is we're going to be looking at the color distribution of M&Ms. So you may or may not know this, but the Mars company claims that the colors are not equally distributed. So if you see at the box at the top, it's supposed to be that 13% of the M&Ms are brown, 14% are yellow. The most common is supposed to be blue at 24%. So what we're going to do is we're going to carry out a hypothesis test to figure out, is that actually true? Or do we have evidence that there is a skew one way or another? Now, we're looking at a whole bunch of proportions. So what we could do is we could do 6 different tests for proportion. Right? We could see, is brown really 13%? Is yellow really 14%? So on and so forth. Why would we not do that, though? Besides the fact that it's not efficient, what is the downfall of doing multiple hypothesis tests? Okay. Do you remember talking about how every test has error associated with it, so you're just compounding error on top of itself? That's why we don't want to do multiple tests. So what we're going to start with is you are going to be counting the number of each color of M&M you have. And then, in a minute I'm going to show you, on Schoology, there is a form, and I need you to enter how many there are. That's why you have the paper towel, so that you can dump it out and count all the colors. I want like whole number of M&Ms, so if you have fragments or something, don't count those. So count all of the M&Ms, and then go on Schoology and tell me how many you have of each color, please. Okay, so we're going to do our hypothesis test together. Number 1, it says take a class sample. So I'm going to give us the numbers right now. There were 123 brown, 180 yellow, 231 orange, 176 green, 204 blue, and 134 red. The total number of M&Ms we had was 1,048. That was a party-sized bag that we split. So. Okay. We good so far? Okay, so we're going to write down our hypotheses for a significance test. In terms of the null, there are 6 different proportions that we are interested in. The proportion of brown, the proportion of yellow, the proportion of orange, and so on and so forth. So here's how our null would look. The proportion of brown should be 0.13. The proportion of yellow should be 0.14. The proportion of orange should be 0.2. The proportion of green should be 0.16. That's a G. That's P of G. I know my G's are hard to read. Proportion of blue is 0.24, and the proportion of red is 0.13. Now, just note I used the first letter, except there were 2 B's. That's why I did BR for brown and BL for blue. I could have just done 1, 2, 3, 4, 5, 6 also. So this is the way the null would look. The alternative is that this is not true. That does not mean every single proportion is different. So the way that we write our alternative is at least one of the above proportions is incorrect. Okay, so what we're going to have to do to find a test statistic is we need to be able to measure how different are the numbers we got from what we would have expected. So how different are the numbers from what we would have expected? Knowing that we have 1,048 M&Ms, do you have an idea of how to calculate how many brown we would have expected or how many yellow we would have expected? What's your idea? Yeah, so for brown, we would take 13% of that 1,048. I don't know what that is. So 13% of 1,048. It's 136.24. And you're going to leave that decimal. So then the yellow, similar idea, 0.14 times the 1,048. That's 146 rather, 0.72. So we're going to notice the brown was pretty close. Our yellow, 180, was a lot higher than what we expected. So let's do the orange. 20% of 1,048 is 209.6. And then green is 167.68. Blue is 251.52. And then the red, that 13% we already did, 136.24. Okay, so this is important, so I would write this down. All of those expected counts, what you did is you took the sample size of n and you multiplied by p. So this blue, for example, we did our 1,048 and we multiplied by our 0.24. And that 0.24 came from the null. Okay, so what we're going to do now is we are going to use those numbers to calculate our test statistic. So that's what we have in this table below. Those observed counts are from above. So that's the 123, 180, 231, 176, 204, and 134. The expected counts are the ones that we just found. So the 136.24, 146.72, 209.6, 167.68, 251.52, and 136.24. Okay, you are going to take a few minutes to fill out the rest of this table. I'm going to do the first row with you. So it says observed minus expected. So I would do 123, subtract 136.24. So I get negative 13.24. Then what I'm doing is I'm taking that value and I'm squaring it. So that is 175.2976. And then I'm taking that value and I'm dividing by the expected. So I'm dividing by that 136.24. And I get about 1.2867. Let's just round to 4 decimal places. Okay, so I want you to do that for the next 5 colors. So do exactly what I did. Observe, subtract, expected. Then square it. Then divide by the expected value. Ultimately, what you're going to do is once you add up all these values on the right, that'll give you your test statistic. So take a few minutes to do that now, please. So in the table is the values that I got. So hopefully you got something pretty similar. Did we? Okay, beautiful. I want to talk about a few numbers real quick. I want to point out the biggest number and the smallest number. This number, so the one for red, is really, really small. Why is that number really, really small in terms of the data? Oliver? Okay, very good. So we expected about 136 red M&Ms and we actually got 134. So super close to what should have happened in an ideal world. Why is the one right above that, blue, so big? So in the context of the M&Ms, why is the blue value large? Michaela, thank you.
There's like a big difference between observed.
Okay, really big difference between what we expected to happen and what actually happened. We good so far? Now that we have that test statistic, we need to calculate our p-value. Okay, before that, 2 quick questions. What value would we get for a test statistic if our sample was very close to what we expected? Well, it would be close to 0. What value would we get for our test statistic if our sample was very far from expected? It would be a large number. For number 5, if our sample was very close to what we expected, then the observed subtract the expected would be close to 0. Hence, when we summed them up, our sum would also be close to 0. I should have said this earlier, but I'm going to tell us now. This value right there, or that symbol, that is called chi-squared. So it's the symbol chi, and then it's squared. The formula is what we just did. We took the observed values, we subtracted the expected values, we squared, we divided by expected, and then we summed all of them up. What's super nice, that's on the formula sheet. Okay, that's what you need to know for right now. I want to show us how to do this on the calculator. We're going to write down a few things and you'll try an example. So I'll show you how to do it on the calculator in a minute. So let's just go to the next page. Here are the things that I need us to know so far. First thing we need to know is how to write the hypotheses. So what we are doing is called a chi-square goodness of fit test. And how you can identify this test is we have one sample and we are comparing multiple proportions. So we have one sample of M&Ms and we are comparing the proportion of blue and yellow and green and brown, so on and so forth. Your null is going to be written as P1 equals some value, P2 equals some value, P3 equals some value, and so on and so forth. All of those proportions must sum to 1. So I want you to notice that we said the proportion of brown had to be 0.13, not 13%, 0.13, and they all added to 1. For our alternative, you just simply write at least one of the above proportions is incorrect. And then the second thing that we have to be able to do at this point is calculate the test statistic. For that, the expected values are n times p. And then for our test statistic, we take the observed, we subtract the expected, we square it, we divide by expected, and we sum it all up. Okay, I'm going to go back on what I said. Before you do this example, I want to show you how to do this on the calculator. So if you watch the videos, you should theoretically already know how to do this on the calculator. The calculator needs the observed values and it needs the expected values. So what I need you to do right now is in your calculator, you are going to go to your lists in list 1, you're going to put all of the observed values. So you probably need to scroll back to your previous page. I don't remember what our observed values, so you would put in 123, 180, 231 for all 6. And then in list 2, you're going to put all of the expected values. You're going to have to look those up because I don't have them in front of me. So you'll have to just go back. So in list 1, you're putting all of the observed values. In list 2, you're putting all of the expected values. So you should have 6 numbers and 6 numbers. And once you've done that, just quit out of the lists. We all got that? Okay, you should probably be able to guess as to where you're going. You are going to go to stat. You're going to go to tests. So stat, tests, you're going to have to scroll down for a while. And then you're going to notice the first one you come to is a chi-square test. That is not what we are doing. We are not doing a chi-square test. We are doing the one right after that, that is chi-squared goodness of fit test. That's the one you want. And right now, it should say observed in list 1, expected in list 2. Does it? Okay, and then the only thing we haven't talked about so far is degrees of freedom. A lot of times, or every time that we've done degrees of freedom so far, it's been n-1. That's not the case here. Not the case here. So this one is different. It's the number of categories, subtract 1. So in this case, 6 M&M colors, subtract 1. So there are 5 degrees of freedom. And then hit calculate. Do you get the same test statistic that we got? You do? What p-value do you get? 0.001. Okay, cool. So that is how to check your answer, or really how to find your test statistic. So what I want you to do right now is we're going to take 5 minutes, and I want you to do this question, please. So you are doing this question. We'll come back together in 5 or 6 minutes, and then we'll take our break. So good luck. Okay, here are the answers. I do not write the null, and the alternative is written here. I write it like I wrote above in a poor color choice of green. I would have written the proportion on Sunday is equal to the proportion on Monday is equal to blah, blah, blah equals 1/7. You wrote it as a decimal, that's fine too. You wrote them separately, that's fine. Alternative, at least one of the above proportions is incorrect. All of the expected values are the same. You don't need to write it 7 times. Take our sample size of 150 and multiply by 1/7. So the numbers in the table we do not use until we're ready to calculate our test statistic. So you should have put all of the observed values in list 1. In list 2, you should have just put 21.4 a whole bunch of times. There are 6 degrees of freedom. And we get a p-value of 0.034. Now, one thing I should have shown us before is if you have a test statistic, you can calculate a p-value using chi-square CDF. Any idea where you would find chi-square CDF? Distribution. Look for it now, please. Because that does come up occasionally. So if you go to second distribution, you see chi-square PDF, which we're not going to use, and then CDF. So ultimately, we end up with a p-value of 0.034. We reject the null. We do have convincing evidence that the proportion of bursts are not equally likely across the week. Not too bad, right? Okay, so what we're going to do now is we're going to use the same data and we're going to put together the whole test. So we're going to do the test from start to finish. So this is your next page. I need us to copy down the numbers that we had from before. The observed were 123, 180, 231, 176, 204, and 134. And the expected that we calculated were the 136.24, 146.72, 209.6, 167.68, 251.52, and 136.24 to give us a chi-square value of 20.448. Okay. So, choose step is all the same things from before. The procedure, like we talked about, it's one sample. We are looking at multiple different categories. So this is called a chi-square goodness of fit test. P of BR is the proportion of brown. P of Y is the proportion of yellow. What word am I missing? True. So the true proportion of brown, the true proportion of yellow, and then I will just say P of O, P of G, P of BL, and P of R is the same for the other four colors. So I'm not going to ask us to define all 6 of them. The hypotheses we already wrote. So our null was that P of brown was 0.13, P of yellow, I think, was 0.14, and so on and so forth. Our alternative was at least one of the above proportions is incorrect. We are still going to use alpha as 0.05 unless we're told otherwise. There's no statistic to worry about, and we don't have to be concerned if we have evidence for the alternative or not. Okay, here is the part that we haven't talked about yet, is the conditions that you have to check. We still have to check the random. We still have to check the 10% rule. And then there's no approximately normal. We just need a large sample. Okay, so random. Why do we have to check for a random sample? What does a random sample allow us to do? Starts with a G. Generalized to the population. Okay, do you think we had a random sample? We definitely did not. I just had one big bag of M&Ms, and we used a single bag. So I'm going to write pretend yes. So we're going to pretend that we have a random sample. And again, the Y is to generalize. To the larger population. Okay, we need 1,048 to be less than 10% of all M&Ms. That's definitely true. Again, though, that is only when you are sampling without replacement from a finite population. And then lastly, all of those expected values have to be greater than 5. All of the expected values have to be greater than 5. So we have those, the 136.24, the 146.72, and all the rest of them are all greater than 5. Here's what that last condition is actually checking. Normally, we are looking, is our sampling distribution approximately normal? That is not the case here. What we are showing is that our sampling distribution follows a chi-square distribution. So this is another type of distribution. We've talked about normal. We've talked about t. This is now a new one. It's called chi-squared. Okay, then we're down to the calculate part. There is no general formula like in words. The specific formula is on the sheet like we've been writing, observed minus expected squared divided by expected. And actually this is the sum over everything. So then what you're going to do is you are going to show some substitutions. So you will show the first one. So that is the 123 subtract 136.24 squared over 136.24 plus ... And then the last one. So the 134 subtract 136.24 squared over 136.24. So our test statistic we already saw was 20.448. And our p-value, if I remember correctly, was about 0.001. We have to make sure that we give the degrees of freedom, which is 5. And then the picture, you will just copy from your calculator. Did you notice that your calculator had calculate and draw? So you'll just go to draw, copy exactly what it shows. And then lastly is the conclusion. So we are going to write a conclusion. I'm going to compare the p-value to alpha. That's what we got, 0.001. Yeah, okay. Okay, so we will reject the null. So we reject the null. As we have convincing evidence I want this next part in context. I do not want us to write that the above proportions are incorrect. That doesn't mean anything. We want to know, do the M&M colors follow the distribution that Mars claims? And we have evidence that they do not. So we have convincing evidence that the colors of the M&Ms do not follow the distribution claimed by the Mars company. And then I do want to interpret the p-value real quick. Assuming the null is true, and in context, that means that the colors follow the claimed distribution. There is a 0.001 probability of obtaining the observed sample or one more extreme by chance alone. Bless you. So that's what you're always going to say, the observed sample, or one more extreme. There's a few other things I want us to write down before we do an example. Any questions for me? Okay. First thing I want us to know is the chi-square CDF. It is always going to be lower bound, upper bound, degrees of freedom. And the second thing I want us to know is a little bit about the chi-square distribution. What you need to know is that it starts at 0. So there are no negative values for chi-square. It is skewed right. As the degrees of freedom increase, the distribution becomes more symmetric. And lastly, this is a big one. Oops. Last thing is all chi-square tests are always upper-tailed. All chi-square tests are always upper-tailed no matter what. Okay, questions for me before you all do your example? Okay, on the next page, there's this box at the top. I don't think we need to fill that out. I would like you to do this full test. So this is what you are doing with your group. Good luck. Answer key in a minute. I want to tell you there are some things that I do differently. So just know that some of your things should look a little bit different. Please make sure you said chi-square goodness of fit test. Make sure you gave an alpha. Somewhere did you write the degrees of freedom? 2 degrees of freedom. I do not write the null and the alternative like this. I would have expected you to write P of red equals 0.8, P of yellow equals 0.05, P of green equals 0.15. We did not list percentages, right? Should be proportions. And then the alternative, at least one of the above is incorrect. It's a random sample that was stated. I don't necessarily think you had to check the 10% rule here. I think there are infinitely many times that you could have taken pictures, but if you checked, that's fine. The large counts. This is the one where I saw a lot of us had the wrong numbers. Remember, your sample you do not use until the calculate step. So your expected values are 160, 10, and 30. They have to be greater than 5. not 10. 5. And then the most common mistake that I see is when people write their work, they use decimals instead of the whole numbers. So it should be the whole numbers. Same thing in your calculator. In your calculator, you're not putting 0.8, 0.05, 0.15. You're putting the 1, 60, 10, and 30. I need the first substitution, the last substitution. You don't need the one in the middle. You do need this chi-square value, the p-value, and the graph from your calculator. The graph, I don't think looks like this. It should have been very skewed to the right with probably nothing shaded because the p-value was so small. So then we would show that our p-value is less than alpha. We reject the null, and we do have convincing evidence the light is not working properly. How did this go for us? It went okay? Okay. My biggest concern with chi-square is being able to recognize it. So that is something we need to pay attention to when we're doing the practice, is making sure we can recognize that it's a chi-square test.